Hey, everybody. So as you can see, we're going to talk about the uniform distribution. Um, and we're really only going to talk about the continuous uniform distribution. I put it in parentheses because we'll just call it the uniform distribution. But there is a discrete uniform distribution, but we're just going to talk about the uniform, the continuous version. So this is a first example of our of working with continuous random variables. So let's just remember what we're talking about here. If we have a random variable, I'll call x, and it's some continuous random variable, meaning the values of x are not discrete numbers, right? It's continuous data, so it can, it's over some interval. There's an infinite number of values it can take on. So something like height is continuous. Things that happen over some amount of time are usually continuous, things like that. When we have a continuous random variable, so where we had PDF tables for our discrete random variables, we're now going to have graphs, right? So here is I guess I'll put in both axes. Let's say I have a set of axes. The horizontal axis represents the data values. Our random variable will come, right? So something like this. This is going to be our probability distribution function. And the way in which we'll find probabilities. So for instance, if I wanted to know the probability that my random variable was between two values, say A and B, if these are two values, two data values, right? I want to know the probability that whatever this experiment is, that the result is between A and B. Then I look to this distribution and I look at the area under the curve between these two values. All right. So obviously I've drawn kind of an odd shape here, and depending on what this function is, the red line, finding this area can be difficult. We won't do anything terribly difficult. The graphs that we will look at will tend to be fairly simple shapes, or if they're not simple shapes, we'll have technology to find the area for us, okay? These areas can be typically found with calculus, if you've ever played with a little bit of calculus. Okay, so this is the red graphs, these probability distribution functions. You can kind of, a good thing to think about with them is the height of these graphs is not showing you the probabilities, but wherever the graph is highest, that's where the most likely outcomes are for whatever the experiment is. And where the graph is low, so those are the least likely, right? So in this case, if we were running this experiment, this is a place we would expect our result to be very, very high probability. Here's kind of a high probability, right? All of these regions. And out at the edges, it looks like I made low probabilities, right? I just drew this arbitrarily, but that just gives us a notion of what these things do. One other thing I want to mention about these, right? So besides the fact that the probabilities are found by areas, that also implies something about this graph, or any of these graphs, that the total area under them must be 1, because that's the probability that any of all the possible outcomes happens, right? If we know something has to be between here and here, well, the probability that one of the things between there happens, or that we land in some region between there, has to be 1, right? So the total area is always going to be 1 under these. Okay, so let's look at the uniform distribution as a specific example of one of these. Okay, so what is the uniform distribution? So a uniform distribution, it's a continuous for us, since we're doing the continuous one. It's going to be a continuous random variable. Okay, and the key feature is that all outcomes are equally likely. Oh, that S looks weird. Are equally likely. Okay, so there's no region of outcomes that's more likely than any of the others. So when we have one, let's start with notation. We'll have X is our uniform continuous random variable, right? It'll be some data, right? So we'll do an example to make this clear in a minute. And the notation we will use is this. We use X, this little tilde to say X follows, and we'll use a U for the uniform distribution. And remember, with these distributions, when we name what it is, things like the binomial and the Poisson, there were specific parameters we needed to know. There were certain numbers that told you, remember, these distributions are falling into some pattern, but we need to know which one in that pattern it is. For the uniform, there are two pieces of information that we need to know: the minimum data value and the maximum data value, right? Because if you know these two, and you know that all the outcomes are equally likely because it's uniform, that tells you everything about it. Okay, let's use this information to draw a graph of this distribution, or draw the probability distribution function for this distribution. So remember how I'm thinking about the graph I'm about to draw. What I want to represent is that all the outcomes are equally likely. And our outcomes, remember, our data values are along the horizontal axis. So let's just put in our minimum is A, our maximum is B. And we said that when we look at these graphs, the highest points are the places that are the most likely, and the lowest points are the places that are the least likely. Well, in this case, they're all equally likely. So we just end up with a horizontal line. They're all at the same height because they're all equally likely. And that is the complete graph for this distribution, right? This is the thing that we're going to use to get our probabilities, which we'll talk about in just a second. One nice feature when we find things that follow one of these patterns, one of our distributions, is we get some information for free. For instance, the mean, or the expected value of this distribution, is just the middle, the average of the max and the min. Right? So if you expect something to be between 0 and 10, all equally likely that if you did this over and over and over again, the average of whatever that is would be 5. Okay. We won't use this one as much, but if it ever comes up, we get the standard deviation for free as well. It's the length of this interval, b minus a squared, divided by 12. Okay, so this just the way it happens to work out. But the mean, the expected value, is one that's nice for us to know. So let's just do one more thing with this, two more things with this abstract example, and then we'll do a precise example, or a more definite example. If we want to know what's the probability that this random variable that we conduct our experiment and the result is between the interval C and D. So we're going to assume that C and D are between A and B, right? When it makes sense to ask about, or we could ask about things happening outside the interval, but the probability of that happening is 0. So if we want to know this probability, then we need to look at this area, the area under the curve between these two, right? But this is just a rectangle. the area of the blue rectangle, right? And we know how to find the area of a blue rectangle. It's going to be the width times the height. The width is easy enough to see, right? It's the distance between C and D. So that'll be D minus C, right? If C is 3 and D is 5, then that distance is 2. 5 minus 3 is 2, tells us how much space between them. So the larger one minus the smaller one gives us the width. But what about this height? So I just drew that line in there, but there's no scale here, so there's nothing to imply how high that line is. But we can use one of the features of probability. We know the sum of all probabilities is 1. And in the case of these graphs, as I said previously, because the area under this curve represents our probability, if we're talking about the area of the whole thing, it has to be 1. In other words, if I think about this rectangle, right? I won't muddy this up. Well, maybe a little bit. Let's just make it very clear. This full rectangle here, that area has to be 1. Okay, the area of that whole rectangle has to be 1. This rectangle also has to have, we know the area is the height times the width. I'm just going to put H for height. The width, in the same way we had D minus C for the small rectangle, this big width is going to be B minus A, and we can solve this for H to get 1 over B minus A. That has to be the height of this in order for the area to be 1, which it has to be. So that gives us the height, which is the same height as the blue rectangle. This a little thicker. And so we get the probability being between D and C is D minus C over B minus A, which is just the area of that blue rectangle. Okay, so that's really all there is to the uniform distribution, more or less. We're going to do one little complication in the example we're going to do next, but it's just rectangles. The only areas we have to deal with are rectangles, and we use this nice fact that the total area is going to be 1 to get our heights of these rectangles. So let's do an example. So suppose, this is a classic kind of example. Suppose we are going to catch a train, okay? So we're catching a train that comes every 10 minutes, okay? And let's say all arrival times are equally likely. So the way I always play this out in my head is our train station is around the corner, and so we don't know, we can't see it until right when we get there. And so when we round that corner, if the train's not there, if we see an empty station, we may have just missed a train, or a train may have not been there for 8 minutes and it's about to come. But we know for certain that its schedule it stays on is once every 10 minutes it shows up, okay? So all the arrival times are equally likely, right? So in this case, that means from 0 to 10 minutes. All right, so we just arrived. One might show up immediately upon us getting there, or we might have to wait the full 10 minutes, right? But they're equally likely, okay? So let's ask a couple of questions. Let's start with 2. How long do we expect to wait, right? And we're asking this, so what we really are saying is what's our expected value, right? In the probability sense. And then what is the probability we wait more than 8 minutes? right? Maybe we need to get to our job, and if the train takes more than 8 minutes to arrive, we're going to be late, right? So 8 minutes is our limit. We want to know how likely it is that we're not going to be late, okay? So let's set this up. We'll start with a random variable. Let's make this a little darker. Okay. So we'll take x to be, let's call it the arrival time for our bus. I'm going to put it in minutes. Okay. And according to the problem, x follows a uniform distribution because all the arrival times are equally likely. Okay. And this is continuous, right? There's any amount of time between 0 and 10 minutes that train could arrive. So all the two pieces of information we need to put for the uniform distribution, we need to know the minimum arrival time, 0 right now, or 10. Okay. And now we know completely this distribution. So let's draw the graph of this distribution. There's a little scale. I'll make it that brighter red. So this time we're starting at 0. I can put 10 out here somewhere. Okay. And there's our distribution. And we already know the height. Let's put this height in because remember the height is going to be 1 divided by this width. Well, this width is easy. We know it goes from 0 to 10. 10 minus 0 is 10. So this line must be at a height of 1/10. So the probability that we expect, that we wait, the expectation. So how long do we expect to wait? Well, that's one of the things we get from our uniform distribution for free. The expected value, or the mean, is going to be 10 minus 0 over 2 equals 5 minutes, right? The way to think about this is when we get there, we don't expect that every time we get there it's going to take 5 minutes, but if we catch this train every day and find ourselves in this situation, if we did this for a month, sometimes the train would arrive right when we get there. Sometimes we'd wait the full 10 minutes. Sometimes it'd be 5.5 minutes. Sometimes it'd be 2 1/3 minutes. All these different times would happen. The average would tend to get closer and closer to 5 the more we did this experiment. Okay, that's what we mean by that statement. All right, so now let's answer the question, what is the probability? Use the graph, but write the work up here. What's the probability we wait more than 8 minutes? Well, how long we wait is dependent on the arrival time. So this is equivalent to saying, what's the probability that x is greater than 8? Okay. And in our little picture, so 8 might be, I didn't count these. Let's see, did I get lucky? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I made 11 of them. So we're going to be about right there. We'll call this 8. So more than 8 means this rectangle here. That probability represents that we wait more than 8 minutes. So the probability that x is greater than 8 is the area of that blue rectangle, which is going to be the width times the height. In this case, the width is 10 minus 8, or 2, and the height we already discovered was 1/10, so 2/10, or 1/5, or 0.2. Okay, so there's a simple computation of the probability using the uniform distribution. All right, had a little hiccup there. Maybe it wasn't even noticeable, but it stopped recording for a second. Okay, let's slightly complicate this situation now. Let's ask a similar question. So let's say we show up, everything's the same. I show up, I know I have about 10 minutes I have up to 10 minutes to wait. All the times are equally likely. And I know if I don't leave if the train doesn't arrive before 8 minutes, I'm gonna be late. So I sit there nervously, hoping it shows up soon, and I wait 3 minutes, and it still hasn't shown up. So now the question is, after 3 minutes, what is the probability let's say, after 3 minutes, what is the probability the train arrives after 8 total minutes, right? So not 8 more minutes, but 8 total minutes. So I've already waited 3. I'm still wondering about being on time to work. And so I'm wondering what the odds are now, okay? So this is a different question. This is a conditional probability. This is the question, what's the probability that the arrival time is more than 8 minutes, given we already know it's greater than 3, right? Because I've already waited 3 minutes, the arrival time has to be greater than 3. It didn't show up in those 3 minutes. And so now the probability is conditional on that, okay? Well, we know how to find conditional probability. So we're gonna do this problem in 2 different ways. We're gonna first just use our formula, conditional probability, right? Let's just, I'll write it up here. If we have the probability of A given B, this is equal to the probability of A and B divided by the probability of B. Okay, so in this case, it's the probability of X greater than 8 and X greater than 3 divided by the probability of X greater than 3. Okay. So the top one's a little bit silly, right? Because the probability that the arrival time is more than 8 minutes and also it's more than 3 minutes is really just the probability that it's greater than 8 minutes. Because if it's greater than 8 minutes, it's already greater than 3 minutes. Okay. So this part here, the probability that X is greater than 8 and X is greater than 3 is equivalent to the probability is that X is greater than 8, right? Another way to see that is if, maybe I'll do this side work. No, let's just do it right here where we can see it. If I was doing X is greater than 8 and X is greater than 3, this is the probability that X is greater than 8 times the probability that X is greater than 3 given X is greater than 8, right? That's just our formula for probability of A and B. Well, we already know the probability of X is greater than 8. We just figured that out to be 0.2, and this is silly. What's the probability we wait more than 3 minutes if given that we wait more than 8 minutes? Well, that has to happen. If you waited more than 8 minutes, you did wait more than 3 minutes, so that probability is just 1. And so this piece is just a 1, so the whole thing is the probability of X greater than 8. So our numerator is just the 0.2 that we calculated above. Now let's go over to this graph for the other part. Let's use, how about green? So now we're looking at, so 3 will be somewhere down here. The probability that X is greater than 3, right, is this whole rectangle. Well, this is also easy to figure out. The width here is 7, the height is 1/10. And so we end up with 0.7, 7 divided by 10, right? And just to make it simple to look at, this is just 2/7. Okay, all right. So that's perfectly good way to do this problem. But let's do it one other way. Once we wait those 3 minutes, we can like think we're in a new situation now, because here let me just write it out and then explain it. If I make y the random variable, the arrival time after 3 minute wait, in minutes. Well, once those 3 minutes have passed, the rest of the outcomes, now there's 7 more minutes in front of us, those 7 minutes are all still equally likely, right? When we started, the 0 to 10 were equally likely, but now 0 to 3 are 0 probability. There's no chance that the bus arrives in those time. We just waited and it didn't, or the train arrived in that time. We just waited and it didn't. So now all of the chance is in those 7 minutes, and they're all still equally likely. So this y still now follows a uniform distribution. The minimum time is the bus shows up right after our 3 minute wait, or goes up to 7 because there are now only 7 minutes in front of us. Right? And our question about the probability of x being greater than 8 given x was greater than 3 is equivalent to the probability that y is greater than 5. Okay, so there's no conditional here anymore because this variable is always starting at 3. That's just the world we live in. There's 7 minutes of time for this train to arrive in. Okay, and being the train taking a total of 8 minutes to arrive is the same as taking 5 minutes to arrive after we've already waited 3. Okay, our graph is going to look very similar. Right, so now it just goes out to 7. There's our horizontal line. The height is now going to be 1/7, right? Because we're going from 0 out to 7. The total area has to be 1, so we can figure out that the height must be 1/7. And greater than 5 means we're looking at this rectangle here. Right. So the area of this rectangle, well, it's easy enough to see this is a width of 2. We already know the height is 1/7, and so that area is 2 times 1/7, or 2/7, which is, of course, the exact same answer we got above. We're just framing the question a little differently, right? It's like we never thought to ask the question in the first 3 minutes, and then we look at our watch and say, "Well, 3 minutes have passed. All right, there's a bus coming in the next 7 minutes. It's equally likely to happen in any of those times, and I need it to show up in the next 5 minutes. What are the odds it doesn't?" Is what we're looking at here. Okay, that is it for this one. Thank you, everybody. I will see you next time.